we shall discuss on language of computers. So how it reaches to a hardware circuit, we must understand that. So from the lowest level, we know that they actually require voltage. Say we can call it 5 volt or 0 volt. But next abstraction, to a gate, we actually convert them to binary values. Binary logic values. So we may say that something like that, say 0.7 voltage is equivalent to logic 0. And say 5.0 volt is equivalent to 1 logic. These values might change depending on the circuit, slightly change, but we can assume that these are the voltage levels for logic 0 and logic 1. Then we group them, these binary bits. So they are binary bits. We group them to get group of binary values. E.g. so 0 1 0 0 1 1 0 0 so on so on so forth. The next stage of language is high level language. Sorry, assembly language. Assembly language. We have seen some examples like this in the last lecture. We have seen these are the assembly level languages. Not exactly following any architecture, just for example, we took this. I shall come to the exact form of assembly language, but these are just representative examples. And on top of, we have high level language, high level programming language. Like you'll see C++, Java, Python, so on and so forth. And then the last level is the language you speak. So if you represent it, say we have binary language So binary logic values, because voltages are same. These are same binary voltages, and these are just replacements. 5 volt is equals to 1 and 0 volt or 0.7 volt equals to 0. But they, you can assume them they are same. So starting from binary to the language we speak. So I shall now write it like this: binary language on top, and here human language. So what we can observe that when you move from binary to human language, complexity increases. Whereas when you move from here to here, implementation in a machine becomes easier. However, we like to prefer communicate in this language. Computers like to prefer communicate in this language. So that's why there is always, you need to transform these high level languages as close to the computer language. Essentially, that will make the machine can easily understand. Okay, but the language becomes more complex. Similarly, the translation is not that easy, since the complexity increases toward this. So obviously, if you try to convert a complex language to a little lower complex language to a little lower complex, you need some method. So that is what actually architecture talks about, so that the implementation becomes easier. So we create circuits that converts human language to binary language, as simple as it is, so that machine can understand human language. Okay. So we have already seen that how a typical assembly language looks like. Okay. But we need to understand that how we can reach from thoughts to machine language through various stages. So we have thoughts. We are thinking about something, human thought, human thinking. So from here, what we get? We get high level program. But who does this translation? This is done by A programmer. Converts the thoughts into high-level program. Now, high-level programs are maybe little close to machine, but they are more close to the human thoughts. So computers cannot understand. Computers only understand machine language 0, 1, 0, 1, 0, 1. There is a component in the system just so the component, the output from high-level program to the next one is assembly language. But who does this translation? Can someone tell me that? Any guess, any idea who does this translation?
Architecture.
No, it's done by compiler. It's a software. It's a software. Obviously, it's an intelligent software. The software knows about architecture. That's correct. But it's not done by someone else. It's a software which converts a high-level program into an assembly language program. So high-level programs like you can see C, Java, Python, all these things. Here you will find assembly language programs like .asm. Like examples I was taking in the last class, which includes move, add, sub, and so on and so forth. Now from here, we get machine language. Which is nothing but 0, 1, 0, 1, something like that, all binary bits. It goes to hardware. Circuit. Now who does this? This one. It's very simple. This is not an intelligent agent. Rather, this is intelligent. I'll say compiler is an intelligent agent.
Assembler.
Yes, this is done by assembler. It is a kind of table lookup based program. Kind of table lookup. That you have a table, on the left side it is written move, on the right side it's binary code. So in modern machines, you will find that assembler becomes a part of the compiler. This one, assembler becomes a part of the compiler. So both these, from directly from high level language, you reach to the machine level language. In between, you do not see assembly language program in the modern systems. But earlier, when compilers were not that much intelligent and optimized, we actually directly converted thoughts to assembly language program. Okay. High level languages were not that much available. So we converted until C arrived. So we converted our thoughts directly to assembly language program, and then the table lookup software assembler, which converted the thoughts to machine language 01, and then it directly goes to circuit. So our understanding for this particular subject will not be only confined within this area. However, if you would like to have good compiler, which is an intelligent software, system software, you need to know the architecture. Otherwise, you will not be able to generate an optimized assembly code which will run on the hardware efficiently. So we shall be dealing with directly from here to here to here. Obviously, the hardware we need to know, because these binary bits will not execute in any circuit. You need to design the circuit depending on what is the hardware, or you need to design the hardware depending on what is your requirement. Okay. So we have seen one type of classification. Now coming back to this hardware designing, we have seen one way of classification with respect to the high level requirements. The 4 classification of machines or computers: SISD, single instruction, single data; single instruction, multiple data; multiple instruction, single data; multiple instruction, multiple data. We have already seen those things. There is another way of classifying the machine based on assembly instructions. Okay. So we shall now do another way of classification. We have 2 different types of machines which are available. They are categories based on their internal design. SISC and RISC, CISC and RISC. CISC stands for complex instruction set computer. This one stands for reduced instructions set computer. Okay. Now so these are 2 design approaches. There are two philosophies. One is CISC, another one is RISC. In modern day processors, they actually combine both. There are certain advantages of CISC, there are certain advantages of RISC. There are certain disadvantages of CISC and disadvantages of RISC also. We shall focus maybe 20 to 25% time spending understanding the CISC part, and maybe 75% to 80% time we shall spend in understanding RISC architecture, because this architecture provides highly flexible design, and this is complex in nature. Though we will understand the philosophy of CISC, but for our design purpose we will follow the RISC principle. Now examples for such machines are Intel series like 8085, starting from 8085, 8086, all the modern machines. Here our focus, so here we will focus mainly on this sort of architectures, whereas in case of RISC we will focus on MIPS architecture, 32-bit. Now let us understand that.
Sir,
Yes.
this classification is based on what?
Design approach. This is based on design approach.
The last class?
The last?
SISD, SIMD.
That is basically based on requirements. Okay.
Okay, sir.
That is based on requirements. Whereas this is design approach. The SISD, SIMD, MIMD, all those things, they are based on requirements. Okay, Flint's taxonomy is based on what is your computational requirement. Okay, so there we also have, we'll have to take either CISC and RISC in those approaches. So design approach is CISC or RISC. Okay, so that's basically how to make parallel computations. That is done based on the Flint's architecture, whether you want to have single computation or multiple computations or parallel computations. Okay, but within the single computation in a CISC, in a SISD machine, you will have to take either CISC or RISC. Okay. Okay. Is that clear?
Yes, sir.
Yeah. So there are some important points which we need to understand here. First of all, what do we mean by X-bit processor? The answer is, inside the processor, this is very important. The conceptual understanding of X-bit processor or N-bit processor is very important, because based on that all our design will follow. So inside the processor, so please carefully look into this. What I am discussing now, that will be very much important for design purpose. So inside the processor, X bit data can flow in parallel from one unit to the other unit. Also, the operations are allowed on X bit data. Now, from these two sentences, can someone tell me that what are the constraints I am putting about the internal modules of a processor? Just read these two sentences and tell me that what are the constraints I am putting or what restriction I am putting on the internal modules of the processor. There are many modules of the processor. Any guess?
The max size of integers that we can do operations.
So that means, yeah, you are going in right direction. So it means you can store temporarily the data of X bit. So your internal storage units will be of X bit size. Anything else? One point is that. What about the circuits of the operations? Logically think.
Anything related to parallel.
Total capacity.
Who is speaking? One by one. Let me. Nandini, are you speaking now?
And anything related to parallel flow.
Nandini, please go ahead.
So I'm thinking about something related to parallel flow also.
No, parallel flow I will have told. Inside the processor, X bit data can flow in parallel from one unit to the other unit. But for parallel flow, what you require? For parallel flow, what you require? You require parallel connections. Is it not?
Yes. Yes.
So from any unit to other unit, you require parallel connections. So if you have one unit here and another unit is here, I'm not talking about what is this unit. These units are. This is C1 component, this is C2. If they are communicating to each other, and as per my understanding, inside the processor, X bit data can flow in parallel from one unit to other unit. So it means if this is a bidirectional flow, something like this will be a X bit line. Now, usually in design, we do not we draw X lines. Rather, we draw a single line, I make a cut and make it X bit. That says that it's an X bit line. What else other than this?
So all capacities and limits must be multiples of
Right,
X bit.
exactly. So capacity of C1 equals to X. Now, if these are internal storage devices, then capacity is a good terminology. What about operations? Say if I have a circuit. Now these are internal storage device. Now, if I have a circuit that performs some operation, what about this? You need a circuit that can perform parallel operations, right? On X bit data. So this circuit also should support operations on X bits. You may question that after performing operations on 2 X bit numbers, the result may be X plus 1 bits. I know that. But those additional bits can be taken care separately. Fundamentally, the capacity of the circuit will be also X. So if we are enabled to make all the internal components like this, then information can flow smoothly from one unit to the other unit. Do you agree with me or not? You can always come up with a design, no, I will make it a double the thing or smaller this. That will unnecessarily complicate the system. But you may argue that your input data may be larger than X bit. Then what to do? Your input data may be larger than X bit. You have an integer. Integer takes 4 bytes. We know that integer takes 4 bytes or 2 bytes depending on the compiler. Let's assume that 4 bytes. Now, if it is 4 bytes, if your machine is 16-bit machine, can you perform integer addition? Simple questions. Your machine is 16-bit machine. Or let's assume that your machine is 32-bit machine, because we shall be dealing with RISC 32. So let's assume that from now onwards everything is 32-bit except 8085 and 8086, which will be discussed in the laboratory as well as. Let's assume that your machine is 32-bit and you are dealing with a long integer. We know that long integer is 8 bytes. So how do you add 2 long integers using a 32-bit machine? Any guess?
We'll take the modulus.
What do you mean by modulus? What do you mean by
We can
modulus?
do addition still also, like it will take double time, like.
Right, exactly. Exactly. Correct. What you are saying, Sushant, it is correct. Say, I will break the larger addition into small additions. Even it can be 64-bit, it can be 128-bit, doesn't matter. My machine supports 32, so I will do the first 32, then keep the result. I will do the next 32, then keep the result. I will do the next 32, keep the result. I will do the next 32, keep the result. And in between, I need to do a processing of the carry. All these circuits actually support those things. So we can always provide solutions for larger computations with smaller facilities. Yes, we agree that it will take time, more time to finish. So our design philosophy tells that we shall maintain all the internal paths x bits, all the internal registers x bit, all the internal components wherever possible, to keep it wherever possible, because not all components require x bit, that we will look into it later stage, but wherever possible we will keep those internal components x bits, so that parallelly x bit data can flow, can be processed, and can come out and come inside the processor. That is the way we define x bit processor. Now this is a very conceptual understanding, I gave it to you. It is up to you, how do you write these sentences. Okay, these are all my creation, you will not find in any book. Okay, you may find the definition of n-bit processor in many ways, but this is what the conceptual understanding of n-bit processor or x-bit processor. Okay, is that clear to everyone? Any doubt? Anyone? Any doubt? Good. If you have no doubt.
Hello, sir. Excuse me.
Yes, yes. Who is
Sir,
speaking? I know.
yeah, my name is Sujit, sir.
Yes, Sujit.
Sir, if it is a 16-bit processor, if the output device is also 16-bit, then we can't add 32 bits, no, sir.
Output device. What do you mean by device?
Output device like LCD segment.
Yes.
Like
So
that.
in the LCD segment, when the output, if the output device is 16-bit, then you'll have to, show it 16-bit, 16-bit, 16-bit. You cannot, handle it more than 16-bit at a time. Right.
And to store the output also, we need two devices, no, sir.
Two locations, rather. Two locations.
Two
Yeah,
locations.
right. Yeah, that's correct. Absolutely right. That we will look into the memory organization. If you talk about storing, okay, memory is the place where we store everything. So if we want to store 32-bit data on 16-bit memory organization, then we require two locations. That's correct.
Okay, sir. Understood.
Anyone, any doubt up to this position, up to this point?
Sir,
Yes, please speak.
Sir Satya Sangra.
Okay.
Sir, in the example that you have shown, like C1 and C2 components, X bit data is flowing and their capacity is also X. So at
Yes.
any point of time, one of the components will be empty, like they will have no data if the data
No.
has already flown.
Now, this is one point. When I'm talking about data is flowing from one unit to the other unit, it's copying. Copying does not destroy the source. Simple logic. We are actually not moving the objects like from here to here. Okay. It's a copy. In computer, it's always a copy. Unless you explicitly delete. Okay. Even if you explicitly delete, that particular value will be a specific value, either 0 or junk, something like that, depending on how the circuit is implemented. But copy means this one is copied here. It means the value will remain here, as well as the same value will be copied here.
Okay, sir.
It's a typical copy that what we actually use in our, everyday life in computers, like copy paste. You copy something from one document, paste it into the other document. The source document does not, lose the content. Okay. Now, moving ahead, let us understand now. We probably have some idea about what is a processor and how its size is defined. Now let us understand what are the internal components, because that's more interesting. We need to know that what is inside, what are inside a processor. So we should now look, deep dive into the processor. So components inside a processor. The components inside a processor, I shall talk about major components. Okay, there are small minor components which you will, when you will design, you know that these components are needed. Okay, so those are not important components, but what I will talk about the major components. Okay, so I shall write down major units or components. Internal registers. These are temporary memory locations. You may say that how many? How many internal registers? That will be decided based on our design principle. That whether it is CISC or RISC, this will be decided. Because if you increase the number of internal registers, it has certain advantage. But it has some disadvantages also. I'll come to those points at the stage. We have one specific unit that is called arithmetic logic unit. From the name itself, you can understand what it does. It actually performs all the arithmetic logic operations. Addition, subtraction, multiplication, and or not, all the arithmetic and logic operations required will be done by this arithmetic logic unit. Third one is the brain of the computer, which is called control unit, or it is called CU. These internal registers are also known as register file. Or RF. There will be many registers. It's not one register, there can be many registers. We have internal data bus, obvious for transfer. Memory interface. Or control unit. Because these are temporary memory inside the processor. A larger memory is outside the processor. So for that you require memory interface control unit. Then we have input output interface control unit. These are major units or components. Other than these units, there will be small components which we shall include as and when needed. And Those are, you do not need to remember them. You will know that when it is required. By experience itself, you will be able to understand that where you require minor components other than this. But these are the major components, vital components, which are really important for a typical computer. Now we shall zoom in further. Let's see that how the internal registers are classified. We have some registers which are called general purpose register. Or in short, it is written GPRs. And we have special purpose registers. Or SPRs. With this, we are now ready to make a fundamental diagram of a processor. Let us now look into the fundamental diagram of a processor, which is very naive, but we need to understand this. Okay. So before I actually go to design a conceptual diagram of a processor, internal diagram of a processor, let me again explain you the functions of these units. Internal registers, they store temporary values. They are called register file. It's not a single one, many registers. What will be the size of the register? In a typical X-bit processor, every register will be of X bits, correct? Arithmetic logic unit, it's a single unit which takes, because we deal with binary operations, so it requires 2 inputs and 1 output. Both the inputs will be of X bits and output will be of X bits. What is control unit? It is the brain. Why it is required? Because you have so many registers, so many other units, which one will act at what time, how the transfer will happen, whether it will be an addition or subtraction or division or multiplication, that will be decided by control unit. Whether to send it to the memory or copy from the memory, whether to send it to the IO or copy from the IO, everything is decided by the control unit. So essentially, this is the brain of the computer. Control unit is the brain of the computer. Now I am not explicitly mentioning that what will be the size of the control unit, though input to the control unit can be made X bit, because the program which initially goes to the control unit and then control unit performs the operation. So the output of the control unit may not be 8 bit always. It may be more than 8 bits, it may be less than 8 bits, or it depends on how many signals are required. So control unit generates all the control signals. So that's why explicitly we may not be able to specify that how many control signals will be coming out of the control unit. Okay. Internal data bus will always be 8 X bit, Okay, because they will be transferring data from one unit to the other unit other than the control bits. Other than the control bits are separate bits. Okay, I'm not talking about data bits then. Data bits are from one unit to the other unit, transfer of data. Control signals are separate signals. So we have two different types of signals. One is, even though the data signal and control signal all are 0 and 1, but category is different. Data moves in parallel, control signals move asynchronously. Okay, I'll come to that point. This part may be a little bit confusing at this stage. But when I'm talking about internal data bus, you assume that it is only the flow of data moves from one unit to the other unit. Okay, and memory interface control unit, interfacer control unit, what it does, it basically acts as an interface between the processor and the memory, external memory. IO interface control unit, it acts as an unit to interface between the input output devices and the processor. Okay, so these are the functions of these units. Now we are ready now to understand how possibly a conceptual diagram is there, internal diagram is there. Okay. So conceptual diagram. CPU. Now, this one can be used as a conceptual diagram of a CPU. So I have included one control unit, general purpose registers, some special purpose registers, an arithmetic logic unit, memory control unit, an IO control unit, and internal bus is obviously there. Now, if you look into this, it seems to be a star connection. Doesn't look like a star connection?
So what does star connection mean?
Star connection is something like this. These are units. Any unit can communicate to any other unit, but probably when one communication is going on, other communication is not allowed. Because when you transfer the value from here to here, the value also reaches here, 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 here. So the bus is busy. Okay. So this is a single bus design where everything goes through a common bus. This is a common bus. So you can actually bring this point, these points to a close one, and then you find it a star connection. That's why I'm saying this is a kind of symbolic representation of the connections here. So when one register is transferring the value from another register, so it happens here. Actually, in real implementation, there are multiple connections here in G registers. I have shown only one connection. In real implementation, you require at least two connections. Okay, that we will see that in the implementations why we require two connections. That's why I told you this is a conceptual diagram. This is a conceptual diagram.
Sir,
Yes.
control signals should also go to all the GPRS, SPRS, right?
Yes, yes. Control signals should go to each other units. I have only shown the control signals here because as if the operations are done here. Actually, operations are done involving every component. I am not showing control signals for other units. Without control signals, these units will not work. Even the control unit will also not work without control signals. So it's a self-driving force. Control unit works as a self-driving force for itself, as well as it drives the entire unit. So it's like your heart pumps the blood to circulate nutrition, and that nutrition circulation also happens within the heart muscle. Probably the best example I can give is your heart. Everyone's heart, what it does, it pumps blood, and blood is pumped so that the nutrition reaches the cells. Now heart is also made of cell. So probably this is the right analogy to understand what is the control unit. So you can interchangeably say that whether it is a heart or brain. Okay, in terms of computers, Because we do not provide nutrition, rather signals, that's why I'm calling it as brain. Is that clear now? So we have a circuit here that not only drives other circuits, it also drives itself. And this process goes on as long as the machine is powered on. That is the beauty of the system. As long as the machine is switched on, this process goes on and it never stops. If it stops, your computer is either restarting or shut down or it has hanged. Otherwise, it is continuously running. There is no stoppage, not for a single pulse, clock pulse. Now the entire circuit is a sequential circuit. That means it works on clock pulse. The events of transferring data from here to here happens at right time. So if you need to incorporate timing information, you know that what to do. We need sequential circuits. That is the reason I told you, recap your digital electronics knowledge, because that is the most important thing to go for designing a processor. You need to understand that what is sequential circuit, how sequential circuits are designed. Okay, let me get your feedbacks up to this point. Anyone, any doubt, anything, any confusion? We shall discuss right now. Correct? All okay? So we have now understood the conceptual diagram. Now let us see that what type of data movement may happen inside this circuit and outside this circuit. So movement of data. Can someone tell me that what kind of movement of data we can have possibly? I can see three types of movement. Okay, just guess what are those three types of movements. I'm talking about data movement, not control signals. What type of data movements?
Register to ALU, ALU to register, and register to register.
But they are of the same type.
So like loading and storing.
You are going in the right direction. So actually, if I combine the answers, then I get the full answer. You are saying that loading and storing. Loading and storing happens from. You'll have to understand.
Registers to
Register through.
See, this is a CPU. This is the CPU. This is memory. This is I/O. Now you tell me, What type of data movement?
IO to CPU
Right. IO to CPU,
and memory to CPU and CPU to memory
memory to CPU and CPU to memory, and
within CPU.
within CPU. Absolutely right. So 3. One is external to internal. External means either from memory to CPU or input to CPU. External. Internal to external. CPU to memory or CPU to output. And third one is internal to internal. These 3 types can take care about all other subtypes. Right? So here external to internal, we call it load or read. Internal to external, we call it store or write. Internal to internal, we call it move. But that does not solve the problem. Here actually we are categorizing broad categorization. It is broad categorization. Now specific categorization has to be done. Now, is it possible if I simply make this categorization, I can ensure that the data will reach to a particular location? What are the other requirements? How do we define a movement? Any movement, how do we define?
Flow of data bits.
Sorry? Can you repeat it?
Flow of data bits.
No, what flow of data bits is, I mean to say, once you place it, that flows. It's an electrical signal, it will flow. That does not require any specific, circuit. It will automatically. You place it on the data bus, it will go.
Address.
Address,
Source
right.
and destination.
Source and destination, right. So the movement is restricted. I told you this is a star connection. So star connection means if you place it, it goes to everywhere. So you need a mechanism so that it only goes to here. That is the reason we now move to the next part, which talks about restricted movement. Every movement is controlled by source and destination. So we write it like this: instruction followed by source or sources. I'll tell you that why sources, and then destination. So if I write something like this, C equals to A plus B. If my high level instruction is like this is high level. The low level instruction can be add R1, R2, R3, where these two are sources, this is destination. And the operation is add. So assuming that A is stored here and B is stored here and C will be stored here. So these two are very important, source and destination. They're very extremely important. We need to find out that where is the source and where is the destination, because you have register files. This registers file may contain 100 registers or 60 registers or 10 registers or 8 registers, 16 registers, 32 registers, depending on whatever your design supports. Now you need to select the right register to get the right value. So the next question comes, where is my data? So it is part of address of data, which is also called addressing mode. The data can be in internal register, the data can come from IO device, the data can be in memory also. We need addressing modes. We need to define addressing modes. And all the instructions, when they are designed, they mention specific addressing mode. Because without the addressing mode, you will not be able to find out the source. Now these addressing modes tell that where are the data and where to store. So there are different ways of explaining that where is the data. That is a part of addressing mode. This will be discussed in assembly language programs. In the lab, we shall discuss more about these addressing modes. But you should agree that without this, we shall not be able to complete the operation. Because where is R1, where is R2, where is R3? Forget about R1, R2. Where is data 1, where is data 2, where is data 3? I explicitly mentioned R1, that's why you tell that, okay, you have already written R1, so go to register 1. So R1 from D1 to R, that is the addressing mode. When I am writing R1 instead of D data, it tells about that R1 stands for register. So I am explicitly mentioning that my data is in a register. Okay. So what we have learned? We have learned that every movement is controlled by source and destination. And the format of the instruction looks like to be instruction followed by source or sources and destination with some other additional parameters that we will learn as we progress. But for the time being, you remember that the format is very simple like this. But while we mention the instruction and the operands, so they are operands. The instruction itself talks about the operation. Here the operation is addition. And the operands talk about that what type of data. So the addressing modes are explicitly mentioned through the operands. Okay, is that clear up to this point? Anyone, any doubt?
Sir, addressing system will be discussed in lab.
Yes, addressing modes, obviously, you need to know that addressing modes, but they will explicitly come while learning the assembly language program, you automatically understand. Okay. Also, I will parallelly introduce whenever needed. Okay. But for the time being, why addressing is important, that you must understand. Why addressing? Where is my data? That is the primary reason that we should discuss about addressing modes. Okay. So, how do we transfer data from memory? We transfer data from memory through instructions. How do we transfer data from CPU to memory? Through instructions. How do we process data inside the processor? Through instructions. So we need to know the format of the instruction. What do we mean by instruction? So the components that I was talking about in the last page, If you remember, I wrote like this. This is instruction. Operands. There may be some other options. These instructions can be of, I'll take some examples only. If we need to know a particular assembly language set, we must know their manual. Like a C programming. To learn C programming, you need to know the programming constructs or programming, different way. How do you declare variables? What are the different types of statements, syntax and everything. Similarly, for any assembly language also, you need to know instructions. Let me take you some examples. So instructions can be move, it can be load, it can be store, it can be add, it can be sub, it can be multiplication, it can be division, it can be branch, it can be jump, it can use, it can be call. These are some examples. It can be many more. So when you talk about instruction, we are talking about these things. They are called operations. Operations. Okay. And they are the next part. Only operation doesn't mean operations require operands. Here actually you require operands. Data. It's not necessarily that each and every instruction requires same set of data. It may vary, but some require one data, some requires two data, some requires more than two. And options fill additional field to do something else. When we shall discuss a particular type of architecture, its instruction set, then we will discuss further on it, how these fields are further divided. This is a generic concept. Now, these are assembly language codes, including the operations and options. Now they are written in English-like language. You can see they are written like English-like language. Like move, by looking into move statement, we can understand that this is probably a movement operation. So it has actually no meaning to a machine. Machine does not understand all these, mnemonics. Machines don't understand this. So in some books you will find that they are called as mnemonic. Mnemonics. 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 But these mnemonics, are human created. You can change the mnemonics. Because essentially an assembler will take these mnemonics and convert into a binary code. Because no machine will understand these mnemonics. So what you need to do? You need to convert this into a binary bit pattern. For every assembly language instruction, there will be a binary representation. So on and so forth. This is machine language. And this is assembly. Now, who does it? We already discussed that assembler, because it's a table lookup only. It's only a table lookup. You write the program in using mnemonics. There is a simple program which will go to the table and replace it by this. That's it. Why we cannot write it? Because these are binary. It's very difficult for us to remember this binary kind of thing. So we do not want to remember these things. There is no point also. So that's why an assembler converts this. So that's why we are not interested to a dumb program that basically simply converts a English word into a binary form. We know that the binary form is not going to change, but machine will only understand this binary form. So when we give the input to the real machine, we give this. And these values, binary values, are loaded to the control unit. One by one, they go to the control unit. And these these binary patterns decide the operation. So these patterns are very important. If you change this pattern, you actually change the instruction. If you change this pattern, you change the instruction. If you wrongly give it, it will give error. So because as designed and any architecture is designed based on these values only. It will not understand anything other than this. Now you may ask that if it doesn't understand anything other than this, then how we are actually seeing all the alphabets, letters, images and everything on the display screen? See, these are not computers where we are seeing. They are input output devices which cannot display 0, 1. They will display a particular pixel, a point, either black or white or a particular color. And every color has a code at the back end. That's a binary code. That's why you see it. Even if you open up a file, there is a text written. The text is written, you just see it as a text. Because let's assume that it is written alphabet A. At the back end, what is there? It's not A. At the back end, there is a binary pattern. And when that binary pattern comes to the output device and getting displayed, then the output device converts this binary pattern to some pixel where the LED is glown so that you see the letter E. But processing is done at the binary. So this must be clear. There should not be any confusion that why we are seeing other things. In the display, in the file, in image, video, in speech, in text file, PDF, whatever you do it, those are basically being displayed to you. But if you look into the circuit where it is working as binary bits. While it is presented to us, we don't understand this binary language. That's why it is presented in a form that we understand. So there is a program which actually converts this, and there is a hardware which converts this so that a corresponding letter is printed on the screen. It's only a hardware circuit that does. Is that clear that how basically the processing happens and what we see? The basic difference we should understand. Then only designing will be easier. When we design a new processor, then we will be able to understand the philosophy of CPU designing, whether it is CISC or RISC, something different. But how it works, why we see something like this, whether we are talking about all these, I mean to say that move, add, load, 0, 1, 0, why it is related? We must understand that. So everything, whatever you do, you write a C program, you open up an editor, start typing a C program. You are typing, obviously your keyboard, using your keyboard, A, B, C, D, everything you are typing. But after you type it, essentially it is stored as a binary form, in the form of binary, 0 and 1. Because your hardware only understands 0 and 1. But we don't understand 0 and 1. We are not comfortable in understanding 0 and 1. That's why we, for our convenience, we are used converters at the end. This conversion happens at the end, at the display part. Very simple thing. If I remove the display from a computer, does it make to any user? Does it make sense to any user? No. But the computer still performs its operation. Think about, you run a program, infinite loop program. Okay, the program is running. Just disconnect the monitor from your CPU. Do you think that the CPU will stop? No, CPU will not stop. If the CPU does not stop, but your display is gone, what does it mean? It means CPU is not at all bothered about it, whether you are able to see it in English language or Hebrew or Hindi or Tamil, Telugu, Bengali, Odia, whatever you talk about. It is working on binary numbers. So when we talk about architecture, we speak in binary language. We speak in hardwares. We speak with the hardware. We talk to the hardware, and that is what, as a computer architect, we must learn. I think that's it. I do not want to complicate things further today, because I have covered a lot of depth. I shall be discussing something on the programming side today in the lab. I'll also show you some hardwares, and the next class we will go into the details of designing the processor. Okay, let me let me know your opinion.
So today we will learn assembly language.
Probably we will start some assembly language programming. I'll show you the hardware
Do we have to
first.
install any software for that?
At this stage, it's not needed. Even if it is needed, it is a 2-minute job. Don't worry about that. It's a 2-minute job only. If it is needed, it will not take much time. So don't worry about that. We shall do something on the hardware first. I will show you the hardware, basic hardware, and then we'll carry on. But up to this point, I would like to know that whether things are getting clear in your mind, because that is very important. If the foundation is not good, you'll not be able to design the circuits. But again, I'm telling you, keep on looking the logisim, because all the concepts that we are discussing, we must design using the logisim. So please, study that simulator, and we shall be focusing more time. We shall be spending more time on those circuit designing using logisim. Right? Any doubt, any question?
Sir, what is difference between load and call?
Load is basically loading a value from memory to the processor. Call is calling a subroutine. Call is calling a subroutine. We shall discuss it later. Subroutine is just separate program. Okay, you are right. You're executing a program. From here, you want to call another subroutine, like a function. Subroutine is a function. In C, we call functions. Okay, it's like that.
Sir, will there be any assignment in the today's lab?
No. So assignments will start from next lab. Today I will ensure you that you are comfortable with the simulator. I mean to say that the assembly language simulators. Then a bit about hardware. I'll show you how the hardware can be used. Since you cannot experience the use of hardware by your hands, I will just show you the hardware through camera. Okay. And then, but that's not very important, because it's just only to get an hands-on experience, but it doesn't give additional benefit. You can learn assembly language programming using good simulators. Okay, they are same. Hardware is only just putting the writing the code in using keyboards. Okay, other things are same.
Sir,
Yes.
the assignment which you gave last time means you just showed four registers were there. And sir, can we use muxes for that?
Yes, yes. Why not? That's why I told you, na, because you will have to now, come up with new designs. You can use multiplexers to select the lines. Okay, when you have multiple registers, I gave you 4 registers. Probably you, without using mux also you can do it.
Sir,
But
that
when
were 32 bits they were, no?
right.
So
No,
it will be
32
completely.
bits means 32 bit is a length of the register. I am not talking about the length. See, length can be 132 bits also. Okay. So that's an
Sir,
extension. Parallel lines are not concerned. Primary concern is that how do we make the units working. Whether the unit is 1-bit unit or X-bit unit, that is actually irrelevant here. If number of units increases, then how do you design the circuit? That is what
Okay,
the
sir.
concern. You will not face any difficulty if I change the requirement from 32-bit to 64-bit. Do you think that it will be difficult?
No, sir. Actually, just increase the bits of muxes also. We can
Exactly. Increase the bits of the input lines of the mux and the output line of the mux. That is the only thing. Otherwise, the mask remains same. The multiplexer remains the same.
Yes, sir. Actually, the last time I was thinking that multiplexer, we have to implement multiplexer by ourselves. That will be like 32-bit will be complicated circuit for us, no?
Right?
So that's what I was thinking. We can just use inbuilt muxes of our logisim.
Right. You can just use inbuilt marks, which are available there. Okay, and you can define their input width, input and output width, data line width. Okay.
Okay, sir.
So that's why I'm telling. When you look into Logisim, you see that what are the components which are already available. There is no point in designing a mux, because multiplexers are already available, demultiplexers are already available, decoders, encoders are, unless you require a specific mux, which you may require. Otherwise, you can use the existing modules now, which are available as library. Why to spend time in designing those simple things?
Yes, sir.